So from hydrogen NMR only, we know that there are three pieces of information we can get. The first one, which you always look at, is the chemical environment. Now, the key thing to look for is look for any symmetry in the molecule, which I have missed up. No, I haven't. I got confused. It is double A. So look for any symmetry in the molecule. So the key thing, so for example, if I'm looking at ethanol, I would expect 3 signals for ethanol. If I have got propane, how many signals would I expect for propane?
2.
2. I'd expect 1 signal for those guys and 1 signal for that. And if I had a highly symmetrical molecule, I'd only get 1 signal there. So that's good. The other thing is look at the chemical shift and use your data sheet to do that. That tells you the type of chemical environment it is. So is it just a hydrogen attached to in an alkane, or is it a hydrogen attached to an OH group? Is it a hydrogen attached? Is it an aldehyde hydrogen? Is it a carboxylic acid hydrogen? They all have different chemical shifts. So that is quite a powerful first piece of information. The next one is intensity. Intensity tells us how many, well, it tells us the ratio of protons. I'll say hydrogen.
Does it matter which word you use?
No. Causing the different peaks. And so the key thing, so for this molecule here, ethanol, they've been a ratio of 3 to 2 to 1. These guys would be in a ratio of, well, it's 6 to 2 or 3 to 1. Now, splitted tells us the number of hydrogens on neighbouring carbons. Now, this uses the n+1 rule. So, if I have 1 hydrogen, so 1 neighbouring hydrogen on a carbon gives a doubler. So it splits it into 2 peaks. So if we now compare that against carbon NMR, chemical environments we get, intensity, why not?
It's always just like...
Okay, it's actually to do with the way that we have to run carbon NMR, that it distorts the ratio, it distorts the intensity. In theory, it's possible, because if you've got, you'd have double the intensity if you've got double the number of carbon. The trouble is that I said yesterday that hydrogen NMR is very fast to do. Carbon NMR is much slower. The reason why is when you excite carbon nuclei into the excited state, they take much longer to relax back into the low energy state. So I have to pulse my radio frequencies much more slower. For hydrogen NMR, I can do, well, I can pass Also, one of the other problems is that there's far fewer of them. In a sample where I've got all the hydrogens are NMR active, but this is carbon-13, and because it's carbon-13, they're very, very rare. So in my sample, there are far fewer carbons than there ever would be hydrogens. So I have to pulse slower, and there's fewer of them, so it takes me much longer to do it. And I have to add chemicals that make them relax, go into the lower energy state, and that distorts the intensity. Splitting? Why won't I see? Do I see splitting in carbon? 13? Why not? Sorry? No, I couldn't. No, it doesn't matter. I didn't see it was split.
Because it's a single peak, it doesn't appear as other peaks. You don't get because it's splitting. I don't know. You don't.
But the definition of number of hydrogens on adjacent carbon, when you've got the adjacent carbon, that's what you need. So you can't.
What is the likelihood?
Oh, it's not likely to have two carbons, are you?
What's the likelihood of having two carbon-13s next to each other?
Not very likely.
Really, really low, isn't it?
So
Hardly.
you're never going to get.
Yeah, so you don't see splitting for carbons because you're not going to get two next to each other. So the first practical aspect is we always need a reference, and the reference that we use for both carbon and hydrogen NMR is tetramethylsilane. And you're right, we use that reference. So it's a silicon, and then it's got 4 methyl groups around it. And the reason we got it is because I've got a lot of carbons, which is good for carbon NMR, and a heck of a lot of hydrogens in there, which is good for hydrogen NMR. So I use tetramethylsilane. So tetramethylsilane is used as a reference for your chemical shift equaling 0 ppm. It has lots of hydrogens and carbons, so it's really useful in the same environment. So for solvents there's lots available, but for we at A-Level use either D2O or CdCl3, where we just replace the hydrogen with deuterium, which doesn't appear in a hydrogen NMR. So we use that. They do not contain H, so do not appear in hydrogen NMR. Label protons, when running hydrogen NMR in D2O, any proton, so any H attached to OH or NH does not give a signal. Yeah. Because they are labeled as well. Anything with an NH or.
So they've all been replaced by the deuterium?
Yeah, they're swapping on and off all the time. Do not give a signal. To make them appear, we run the spectrum in CDCl. So to make them appear, run the NMR in CDCl, and that stops it.